I'm going to talk about the properties of waves. So let's start with some definitions. So we have a definition of a wave is an entity that transmits energy but not matter. So one way to transmit energy would be to transmit matter. So we could take a ball and throw it to a friend. We'd be giving them energy through the mechanism of transfer of matter. That's not a wave. Okay, transmitting energy through a wave. We have light waves. We have sound waves. Waves on the ocean, waves in strings, lots of different examples, and all of those transmit energy without transmitting matter. Now, that's kind of a strange definition. So one sort of informal definition that I'd like to think about is that it is a collection of oscillations. So that's perhaps something you're familiar with, and a lot of the mathematics behind oscillations apply to waves as well. Okay, so a lot of the terms or physical parameters that apply to oscillations also apply to waves. So say you have sound waves. When I'm talking here, I'm causing the air molecules to vibrate back and forth. So or at least the pockets of air are oscillating, and so it's a collection of oscillations in the air is what sound is. Um, so another set of definitions is the distinction between what are called transverse versus longitudinal. And transverse waves are waves that where the motion of the oscillations is perpendicular to the direction of the wave velocity. Okay, so let's say you have a piece of string and you set up a wave in that piece of string. So say we're over here, we're lifting up the piece of string up and down, and the wave gets transmitted left to right. That would be considered a transverse wave. Okay, and so the particles themselves that constitute the wave are oscillating up and down, while the wave energy is moving left to right. And then longitudinal would be an oscillation parallel or anti-parallel to the wave velocity, the direction that the energy is getting transmitted. So one example would be sound. So when I'm talking here, I'm generating vibrations this way, and the energy is being transmitted in the same or the opposite direction as the oscillation of the air. Okay, another example would be, say, a spring that you take and push and pull on. Okay, so maybe it's on a table somewhere and you just walk up to it and push and pull on it, and it ends up looking like this. We'll have stretched out areas, compressed areas, stretched out areas, compressed areas, etc. Okay, so we're over here grabbing the spring and going like this. Okay, so the coils within that spring are oscillating left to right, and then the wave energy is being transmitted to the right. Okay, so parallel or anti-parallel to the wave velocity. Okay, so because a wave is a collection of oscillations, a lot of these parameters that we would describe with the with a for an oscillation apply to a wave. So, for example, let's say we've got this. This is, say, a piece of string, and that dotted line represents what the string looked like before we went up and grabbed it and pulled it up and down. This distance here, the maximum distance from equilibrium, or this distance here, that would be the amplitude. So that same stuff from oscillation still applies. So A would be amplitude, and then we have some spatial parameter, or sorry, some temporal parameters, which are period, frequency, and angular frequency. Okay, so those describe an oscillation. But in addition, there is a second spatial parameter for waves. So the second spatial parameter would be the wavelength. So we have an amplitude, how big the oscillations are, and then the wavelength is the distance between peaks or troughs, and we measure it in meters as we would the amplitude. So for the wave on a string, it would be this distance here. That would be the wavelength, Greek letter lambda. And then for the spring, we could go from, say, two compressions and measure the distance between those, and that would be the wavelength as well. Okay, so peak to peak distance, trough to trough distance, that's your, or compression to compression distance, rarefaction to rarefaction distance, that's your wavelength. Okay, and then there's a mathematical abstraction for this parameter, which is kind of akin to the angular frequency. So angular frequency is a mathematical abstraction. So even if you don't have something moving in a circle and you can't measure an angle, you can still calculate an angular frequency. So a mass on a spring bouncing back and forth, that's the angular frequency inside the trig function. It's not a literal rate of change in an angle. And so another sort of mathematical abstraction that goes inside some trig functions is the wave number. Okay, and letter K for that. So wave number calculated in radians per meter. And just like the angular frequency, it's not something you can walk up to a physical situation and imagine using a protractor or a meter stick or a stopwatch to measure. It's something that we calculate based on the wavelength, which you could conceivably measure with a meter stick. You go to the ocean and stretch out a big tape measure and measure the distance between the swells. That would be the wavelength. But then you could calculate the wave number as 2 pi over the wavelength. Okay, so once you have one of these two, of course you should be able to calculate the other. Just like with oscillations and waves, once you have period frequency or angular frequency, you should be able to calculate any three of those. Okay, one more thing is the wave velocity. So this symbol is a little bit ambiguous because there's really two velocities going, well, actually an infinite number of velocities at any given moment, but the symbol V can refer to how fast the energy is transmitted, or if we watch a crest, how quickly it's moving, or a pocket of air that has a high pressure, observing how fast that's moving. So V, but it could refer to the speed of the wave, or it can refer to the speed of the oscillation. So if you think about oscillations, so this little piece of string is bouncing up and down. It has a velocity in a given moment, as does every other little piece of string. But typically when we were talking about waves, if it's not specified, you're probably, the symbol V probably refers to the speed of the wave itself, not the speed that the individual particles that constitute the wave are moving. Okay, so kind of three ways in terms of a spatial parameter and a temporal parameter. I think the most intuitive one would be distance over time, wavelength over period. So distance between crests, time between crests at a given location. So wavelength over period, we can do wavelength times frequency, or in terms of these mathematical abstractions, angular frequency and wave number, it's the angular frequency divided by the wave number. Okay, one more thing to think about is sometimes you don't have to do this, and actually sometimes you know what V is based on the physical construction. So if you know it's sound in normal air, maybe about 343 meters per second. If it's speed of light in vacuum, about 300 million meters per second. So sometimes this number is known by the property of the medium. Okay, so strings, you can predict that based on the tension in the string and the mass per unit length. There's a formula for that. So this V is a property of the substance. So air has the property of transmitting sound at 343 meters per second, for example. Okay, so that's it. That's some general ideas about waves. I'll do some examples that include some numbers, so we'll quantify some of these things. Okay, thanks for watching.